I'll be spending the next half an hour or so talking about what keeps me busy and what keeps me motivated, and that has all to do with testing and the focus of power electronics dominated smart grids. We are at a electric vehicle event, power quality event. For my presentation, I will run through a few aspects. Not that much EV, we are touching it, but we have to take one step back and see what EV charging infrastructure also needs to be able to work. And that is, of course, the biggest man-made system ever built, the electrical grid. So behind all the chargers, behind the infrastructure, we still need the energy grids, the power grids, to be able to run the EV infrastructure that we want and is already being rolled out, of course. So this presentation, keep in mind, is from a grid perspective and might be a bit different than the others in this event. I hope still interesting and relevant, though. Looking at what I'm going to cover, short introduction on where this comes from and what you will be hearing in the next few minutes. We'll be going into more depth into what we like to call system testing, and I will introduce the way or the path towards that during the slides. What we have at this moment to be able to do all the system testing, and then a case study on an ultra-fast charging station that binds everything together and why this is relevant. So, as mentioned, grids and power electronics dominant grids. We find power electronics in all shapes and sizes. For those of you that haven't seen them, yes, you have. You might just not have seen them or not know that they're power electronics. Cell phone chargers, it's an old picture, but it resembles a charger that we all have. These days, we all want a white one instead of a black one, but still 230 volts to a lower voltage done by power electronics. It makes it light, it makes it cheap and efficient. We have bigger units for bigger applications. We have household PV inverters, battery inverters for storage coming up. They go to central inverters, of course, grid connected for community charging or community battery storage, energy storage systems, and of course, the big guys, the HVDC converter stations that link countries together and transfer and transmit massive amount of power. So power electronics is available today and has been for quite some time already. That's not new, but is being applied more often, more frequently, because of its flexibility and the functionality it offers. So what we are seeing in the electrical power grid is that where we need flexibility, and we want flexibility due to the changing nature of our demand and our applications that we run from our electrical networks, we see power electronics coming in at every level of the grid, performing different functions. As you can see here, a picture from the IEEE, the ubiquity of power electronics. Basically, it will be everywhere. You might not even notice it, but there will be power electronics at all levels and parts of the grid, keeping everything alive, stable, and hopefully at the power quality and the reliability level that we are accustomed to, or hopefully even better. So if we dig into that, what does that mean? It means power electronics everywhere. It means that the power electronics and especially the control aspects associated with the power electronics will start to dominate the behavior and characteristic of the grid itself. So the behavior will not be passive components anymore. It will not be a passive system that you can easily model. There will be complex, higher order components in there running with control systems that are non-linear, running the show. And this is if we have this, and there are no numbers on when this will be reached, but at some point, the control systems of all these active devices will actually determine what the grid would be like and how the stability will be assessed. And that is the point where we start talking about power electronics dominant grids, where they have the majority of the share, and therefore they need the most attention from a reliability and availability point of view to be able to provide the electrical energy to all the customers that we have today. It's happening, not from the last few days or years. It's been happening over a longer time, and it will continue to happen. So this is what we are preparing for. And we are gathering tools and methods to be able to handle this. And luckily, we can do that. But we need to rethink how we look at power delivery and electrical grids. So we now have to take into account other phenomena, other frequency components, and other behavior that might not have been necessary before or in classical electrical grid lectures that we've seen before. So here, some warnings already taken from an Aalborg course. You can see there we're talking about resonances. That's suddenly an important topic to take into account. Not that easy to predict anymore, so that needs some attention. Harmonics, of course, we're on a power quality event, so we are going to talk about harmonics. Originating from power electronics, might be mitigated by power electronics. At least there's an interplay between all of this in higher frequency components in all the classification of harmonics that we have devised amongst ourselves. And then, of course, because they are active control systems, it's not just a passive modeling exercise that we need to do, but with active control, there's also coupling between controllers and active interaction and possibly oscillations, which we have to take into account. So these are the challenges or the opportunities that we have when we apply power electronics and its flexibility in power grids as much as we would like to. You can also look at it from a different point of view. I mentioned power electronics and especially the controls. You can also look at this, that the power grids, the distribution grids, transmission grids at some point will transform into what is known as a cyber physical system, which comprises basically two parts. You have the hardware component, which processes the power and of course needs to be capable of the application and the purpose of which it was intended for. And on top of that, a part of control and communication to others, which binds us to a cyber realm. And then the cyber physical systems means you bind these two together, and together you'll have a system that runs on hardware that's capable and software components that make it stable, available, give us the ancillary services or the functionality that we want from the hardware. And this might change over time, of course. So this is something we see more and more often, that we should now look to grids not as passive components, as inductors, capacitors, and resistors anymore, but more as a cyber physical system. And that is a whole new domain with whole new challenges, but also a set of tools that we can apply to make all of this work together again. When we look at power electronics, we also look at different timings and frequencies. Depending on what your application is, you will have influences of these devices on the grid on frequencies other than the power frequency. Of course, the 50 Hertz is what we're mainly interested in AC grids, as long as AC grids exist. But applying all these power electronics will mean there's going to be influences on other frequency components, depending on the rate of switching. Of most of these power electronics have active switching, especially the voltage source converters. And there are control aspects, so the speed of control loops that provide certain characteristics on certain frequencies within the spectrum of the grid. And now these, with power electronics dominant grids, cannot be ignored anymore. There are not, the inertia in the system is not enough to damp out all the parasitic effects, which they were before. They become significant, they become dominant, so we have to take them into account before. And in a few slides here, I will also show you how you can correlate some of these effects or parts of the control system of a power electronic system to parts of the frequency. So there are some tools to guide us through this complex engineering task that we have. And at the bottom here, you can see in which time frame, which name we have given the aspect, so that the harmonics, near synchronous oscillations, subsynchronous oscillations, all these things, depending on the frequency that they operate on, have gotten a name, which you will find back in literature and in some of the standards governing these type of aspects. To look at how to tackle this, of course, with power electronics, you need to model just as you would classical passive component, grid components. You have Norton or Thevenin equivalent of that. With power electronics, there's also the added complexity of what are you going to model as the actual device or the converter. And of course, it's easy to just have a simple model also for the computational effort as a Norton equivalent here as ideal current source, and then start using that in simulations, and then together with the rest of your network model, try to predict stability and resonance points and harmonic oscillations. But we have seen that if you go too basic, you will have, or you will miss some important aspects of the modeling effort in the frequency ranges that are now becoming significant, as mentioned. Therefore, your modeling effort also has to increase. So you have to increase more aspects of the high frequency behavior of such a converter. And one strategy of doing this was looking at the input admittance of the inverter. And this is something you can derive and also measure at some point from a real system, and include that in your modeling to be able to predict more accurately resonance points and also the impedance of such a converter in a larger grid system, and thereby look at the overall stability of the system and the impact of adding more and more converters into a grid system. It's not just the electronics itself, it's of course a combination of the converter together with what it's connected to, circuit theory, nothing new here. So it's also important not to just have the inverter modeled, but also look into what it's connected to. And here the devil is in the details. If you have a cable connection or a transformer connection at the higher frequency components, which become significant for converters, as said before, you also need to model these components in that frequency range to be able to predict and simulate these aspects as well, which means your whole exercise becomes more complex, but it needs to be realistic and to avoid any nasty surprises if you go into real life and deploy such systems. So this is the message here. More homework to be done when looking into a power electronics dominant grid situation than might have been necessary before. This brings us, as mentioned, to a more system approach. So from the KEMA Labs point of view, and especially the FPGLab Lab, we are looking into system testing, and I will tell you a bit more about what we mean with that. This is an aerial photo of the KEMA laboratories in Arnhem. Complex campus, I should say, of more than one laboratory. We have a high power lab, high voltage lab, and the FPGLab Lab in there. And up to now, basically, what these labs do on grid compliance is basically do type test certificates on components. And KEMA has been doing this for 90+ years. We bring out type test certificates on components that are being used in electricity grids, T&D equipment, based on a standard, an international standard that has been agreed upon and is valid. We can do the testing on that, and if you pass all items, you get a type test certificate, which for a lot of equipment means it's the key to the market and you can start selling them and they should work in the grid. That is all based on components where you have a predefined standard and a checklist on which you can do the testing and see if something complies or not. If it does, you get the label, it complies to standard. It does not mean that this component would actually fit to an application or the intended application has been considered in the testing. And of course, if you do testing and the standards are written like that, it has to be general, which means you lose the specific aspects. But once we go to power electronics dominant grids, that is not sufficient anymore. Of course, the component testing needs to be done to ensure that everything is good to go, reliable, and the material will not suffer. And I mean the material the equipment is built of, it can withstand short circuit currents, and the voltage, dielectric materials is fine, all of that. But you have to go one step further, and now you have to check if your component, especially if it has an active control system, will fit into the application it's intended for, and the application is usually not standard or general, which means you have now to include specific application information, add that on top in some form or another, to be able to say if a component together with other components are fit for purpose to work together in a system. and that includes interoperability and all of these aspects as well. But we are trying to ready the process here to go further than component testing and enter system testing. And you can already start to feel that this is a more complex situation, more specific. You have to know more about the application, and you have to do other type of testing, and you need different boundary conditions to be able to validate if something is fit for purpose. We like challenges, so this is what we're aiming for. We feel that because we can't just build bigger labs and bigger labs and bigger labs, we have to think smarter, which means we have to incorporate advanced testing techniques. And we feel that hardware in the loop, which I'll talk about a bit more about in a minute, gives us an opportunity to be able to do these system validation tests in a manner that is still acceptable in real estate and in complexity to be handled by a laboratory, let's say, a defined smaller laboratory with the resources at hand. So this is a tool that we will be exploiting quite significantly in the efforts to get to system level testing. So what is hardware in the loop? Hardware in the loop is just basically connecting hardware components that we would like to test or provide boundary conditions to be able to validate system responses from either the control system, the software, or the hardware, or a combination of, with a virtual world created on suitable computer hardware, usually called real-time simulators. So these exist. You can do the modeling in real-time simulators. You have the real device, and now the challenge is to connect these two together in such a way that they do not interfere with each other, that they provide a realistic connection, and that you excite them in a realistic way that would be exactly the same as a realistic situation fitting to the application would be. And that is where the challenge today still resides, in how we connect the virtual world to the real world without them knowing of each other. It is, however, also the opportunity that we have, if we get this right, to have infinite control over the world around a test object, as we call it, a device under test, to be able to test everything that there is to be tested on the hardware, the software, and the system aspects. So this is the utopia that we are heading towards, to be able to marry these two worlds and then do whatever we can do before we go into the real world as realistic as possible. And if you look into one device, one simulation, that's one level of challenge. If you add more real devices, that's another order of magnitude of complexity. And if you look into different applications, you also look into different time domains that needs to be coupled. So then you have to start looking at different methods of connecting simulations to each other. So then you enter into the co-simulation domain, where mechanical time constants, electrical time constants, and thermal time constants are being managed together in a simulation environment or emulation environment that keeps everybody happy and gets a realistic system test up and running. The idea behind all of this is still the same as it was 1995 years now, to check grid compliance, to see if all of this will work together in a grid context, and that the grids remain reliable and available so that we have the power that flows through them. If that was a bit too much, I have a lower level look at what hardware in the loop testing is. The basic concept is you have a grid, you want to connect something to it. Let's say renewable energies, wind, PV. You connect this via inverter. If you want to do testing on this to see if the whole inverter and the applications are grid compliant, you need a grid. You need the loads, and you connect them together and you see if they work together. This, of course, you can see in the real field is risky, costly in time and in money and resources. So you would like to do this in a lab environment, which means the grid part you exchange with the virtual world. The load part you exchange with the virtual world. Of course, you marry them together as good as you can. And then you can manage the tests of the system level tests in a laboratory that is not bigger than a normal laboratory today. That's the basic concept of what we're aiming for. We want to capture dynamic behavior, interaction analysis, something that's not done with type tests usually. Of course, grid code compliance has fault write-throughs, and those are becoming more and more stringent. as we go through voltage excursions, frequency excursions, and the real life characteristics that we see happening today already. And all of this is, of course, to de-risk the equipment itself and the system before you go live, but within the physical limitations of laboratories that we have today. We are not alone in this. We are part of ERIGrid project that now got an extension into ERIGrid 2, a European-funded H2020 project that covers what I mentioned just now in hardware in the loop and system level testing, and brings it to another level, the holistic testing approach, which also connects even more components to the whole testing environment. Not just the power system analysis and the control system that I was talking about, but also communication, the higher level grid control, SCADA systems, HMIs, all these type of things. It's a 4.5-year project that finished April this year. There's documentation and test descriptions available to guide you through these complex testing scenarios. That's available already. There's a handbook on nomenclature on what you should call what to be able to still make sense out of all of this when system testing is involved. So know that these things exist and that there is a broader network of people looking at this to be able to make this a reality. So what do we have in Arnhem for doing this already today? We have the FlexPower Grid Lab, which, if you can read the boilerplate there, says we're looking at cyber physical systems, which I explained, and we're looking at power cybernetics as a collective argument on how we want to apply hardware in the loop to do system level testing. Going a bit faster due to time. We have equipment there that covers the distribution level quantities that you would need from an electrical point of view. We'll go through them quickly. So medium voltage, 1 MVA of power, or AC and DC. Harmonic control, so we have high bandwidth amplifiers running to be able to do harmonics and power quality events. I'll have to run through this a bit quicker due to time, but there will be handouts available to look at this later on. You can see we have the AC capabilities, grid simulators, high bandwidth, low power, high power, limited bandwidth, 1800 hertz, to be able to create all the AC grids we want. We have DC capabilities that we include as well. Could be PV emulators, battery emulators, EV emulators, also high bandwidth and lower bandwidth but higher power. We have some passive loads. Sometimes you can't get around that. And we have the brains behind it. So the Opal RT is our real-time simulator, but you can have different ones, of course, connecting all of this together to be able to provide the boundary conditions and excite the test as you would like. We're also getting an EV vehicle emulator that fits into discussion here to be able to get EV chargers, the fast chargers, up and running. Quick example on what we did already, microgrid systems, not on the EV. If you look at a microgrid system, there's an application we did about 1.5 to 2 years ago, where you had a whole distribution system offshore that needed to be validated. We did this in a power hardware in the loop setup where you did not have to have any of the generators or any of the loads and still validate the control concept by using power hardware in the loop. So you have the inverters, but all the loads and generators are simulated, and you could still have realistic emulation results to be able to see under which circumstances and which corner cases you need to look at controls and to design and specify requirements for the individual components to be able to engineer the system without any copper or cables being made or components being made yet. So a quick case study. I only have a few minutes on ultra-fast charging stations. Now we come into the electrical vehicles domain. Ultra-fast charging stations, of course, give you the benefit, and this slide is a bit old, needs to be updated, looking at hundreds of kilowatt charging stations to basically mimic what we have with gasoline cars, fuel up in a few minutes, and there you go. Which means the charging stations will go up in power, the charging points will go up in power, and of course they are all power electronics as well these days for the active control and to be able to be efficient. You can see a generic topology in here, which might be how these charging stations roll out. I'm not saying this is what's going to happen, but it's an example. Might be with battery storage closely connected to be more efficient or not. These are options that the market will determine. but you see 250 kilowatt slots and then adding up to active front ends of multi-megawatts, basically. If you look at what these power electronics mean to the frequencies of the grid, I mentioned that in the beginning, we are now looking at different frequency components instead of just the fundamental frequency. You will have to, and you can see the color coding between the blocks of the control and on the left, what it means for the frequency component in the grid spectrum. You will need to take into account more aspects and look at different frequency components in your grid study to see how you integrate such charging systems into your grid, especially if they're next to highways, behind long feeders, far away from transformers. You will excite different frequency ranges. You will have different resonance points, or connecting more of them will change the resonance characteristic, your impedance of your system. And there's not enough time to go into detail here for everything, but there is a dissertation that a former DMVGL colleague of mine at TU Eindhoven finished in end of 2018, covering all of this in detail. So if you are interested in that, there's more to read on how you get to all the equations to be able to model all the aspects that you need and to know which frequency components are significant. It's based on input admittance, so I won't go through this. The whole method is described here on how you get to the input admittance of the power electronics, how you include that in your grid study to be able to capture more resonance points and influence of the control and the power electronics within a grid model to be able to see what it will do on the grid once it's running. The case study has been done with a grid here in the Netherlands, Bronsbergen, which is a famous case study for students at TU Eindhoven. There's a lot of information available there, where a big charging station has been introduced into the network, and further on in the network, it has the frequency spectrum of the grid in terms of resonance has been looked at. And as when you look at this plot on the left-hand side, you can see that there was a resonance point at 1.6 kilohertz with an amplitude of 550 ohms. If you introduce 10 charging stations at a different node somewhere else in the network, at that point, your frequency dependent impedance of the network changes. Your resonance point drops down to 1250 hertz, and it has a positive damping effect. It's not all bad, it's just different, of 51 ohms instead of 550 ohms. But these are the things that if you take into consideration the power electronic modeling and you know what you're doing, then you will be able to predict what the grid will be doing, and there should be less surprises when introducing big active loads, in this case as ultra-fast charging stations. There's a whole study and a few papers behind this if you want to have a look. And for all you Monty Python fans out there, and now for something completely different, there is opportunity in this as well. As mentioned already, we are part of the ERIGrid project. There's 20 plus partners involved in Europe in this European funded project. It got an extension or a second chapter. We're now in ERIGrid 2, which continues the transnational access program, which means that if you have heard in the last 25 minutes or so something that you also want to try, but you don't know how to get into the lab to test things, or you don't have the means to do research in the facilities here, this program provides you the opportunity to get into not just the Flex Power Grid Lab, but other connected ERIGrid labs for free. The only thing you have to do is write a project proposal. It has to be approved by the project, and once it gets approved, all travel expenses, stay expenses, and lab usage is then covered by the project itself. The only condition is that you can't go into your own country, as the term says, transnational access. It means you have to go to a different European country to perform your research in one of these facilities. So if you're outside of the Netherlands and you want to come to the Flex Power Grid Lab, that's one way of doing that. Please look at the website for all the other labs, and you can see some deadlines on when calls are happening, when we are accepting project proposals. Please make use of this. It really is free. There's no catch behind that. It sounds strange in these times, but it really is. And that's the opportunity I want to end with, hopefully still a bit in time. I would like to thank you for your attention. I couldn't see you all, but I'm sure you were listening carefully and have a lot of questions, I hope. And I provided some insights on what is coming our way in terms of power electronics dominated grids, what power electronics means to the grids, and that EVs, especially the charging infrastructure, is part thereof. And the better job we do with integration of EVs, the more this becomes a reality sooner rather than later. Thank you very much.
Oh, great. Thank you, Erik. A very interesting presentation. And I also believe that the invitation you sent to our attendees is also very interesting. I hope a lot of people will be able to join that invitation and to use your lab to their yeah, that's great actually. So I had a question myself, because doing these hardware in the loop testing, you're simulating the power grid. And I was wondering, do you simulate, like, do you first take measurements of the local grid where the device is going to be installed, like the wind turbines or whatever, and you use that in your simulations? Or is it more like you create like a best and a worst case scenario in the grid and test the ability to integrate that device that way?
Okay, thank you for your question. It's both actually. If you have grid data for the application that you want to check grid compliance for, that's the best case, and then you can use the model, the more realistic model, in your hardware in the loop test setup, and then do a very good fit for purpose analysis. Unfortunately, in practice, we see that this data is usually not available. If there's new greenfield sites, then there's no recordings at all. So then the best you can do is use the grid models at that point that you get from the grid operator at that point during a certification project, basically. If even that is not available, then you revert back to more general grid topologies. And for academic purposes, you can also go back to the IEEE dismount bus system just to have a quick start somewhere. But the system is not limited in complexity, so the better models you have, the better results you get. But it's usually getting those values, those models, is usually the tricky part. So that means we're ending up with something in between, and you have to make some assumptions to be able to continue.
Okay, yeah, that also sounds like an invitation to the people from the grid operators to measure a lot of things in their grids, high frequencies, and get you the input you require. There are also some questions from in the chat I see. There's some questions related to if you expect that the grid will be going to direct current instead of asynchronous current in the future.
It is an option, and if you follow what's happening in DC grids, there's potential in there. It is still a question of what do we do with the capital of the AC grid that we have. I started with the slide of the biggest man-made system already. So it has potential for certain niche applications, but rebuilding everything into DC might just be a too long shot for where we are standing today. And that's my opinion at looking at what is a practical result. From a power electronic dominant grid, it does not make any difference if it's AC or DC. The converters usually can do both. It's a matter of engineering everything around it. So the classical components and the meters and things like that you have to think about. But in a power electronic dominant grids, you might have the choice to go into DC in more parts than you have now, at least. And there are some research projects looking into that, to refurbishing some links into DC or to add more DC parts to a medium voltage distribution network or other parts. But it's an interesting question, and yeah, I don't have the crystal ball. I don't think anybody has, but we should not disregard DC. Because of HVDC, we have that as well. It's a viable technology and costs are coming down, but it needs to find its application, and we should not throw away the capital that we've already spent together with the infrastructure that we have.
Yeah, excellent. Thank you. And then we have two questions from Sharmista. This one might be the most interesting. Oh, sorry. Oh, yeah. Okay, we've got 2 minutes left, so well, that should be also the final question, I believe.
If it's yes, no, then I can do it.
Yeah, well, I think it might be a longer answer. it actually says, does it mean that many electric, where did it go? Oh, sorry, just a moment. It was related to the resonance effects. Yeah, does it mean that many EVs interconnection change the grid resonance frequency to a lower level? Can we predict the effect of 10 or 100 EVs charging at the same time in relation to grid resonance frequency?
It's almost a yes/no question. Yes. Yes, the voltage source converters, that's what the study of Jensen came up with, or I didn't invent it, but it highlighted that if you look at the input admittance of voltage source converters, which are the topology that we will see more and more often, you have a capacitive behavior from these devices, which means it compensates for your inductive behavior of lots of the distribution grids that we have. And that moves the resonance frequencies usually lower. And that means you will be able to see them, or resonances, pop up closer to the fundamental frequency. But you can, if you look at some methods here, which I unfortunately had to fly over due to time limitations, there are methods, if you model them accurately and take them into account, then you can look at them during your grid modeling. Your power flow models that you have will not suffice. You have to go into EMT and invest some more time and resources in modeling of all these devices to be able to get this information, but then it's there. And that's the message also from that dissertation, to say, I think now's the time to go that level deeper, because otherwise you will be missing significant parts, and therefore you will pay the price in damages, basically, or misengineering at some point, if all of these extra power electronic components are added without any consideration. And I'm not saying they're not being considered today, but they might need more attention if they become more and more significant. And it's a 1 megawatt here, a few megawatts there, but they're adding up, and they're creeping into the grids that we have today. And that's the message too. Yes, we have the tools, let's apply them,